All right, so guys, here we go. So, in keeping with the spirit of the way that we are going over chapters 8 and 9, guys, the reason that we're doing a KWL for chapters 8 and 9 is, one, it's all conceptual. It is not mathematical at all. Find that a lot of the material, especially in chapter 8, goes in the K column. A lot of this is review. So, with that said, guys, do this with me. Grab your books. You're going to need them today. So, guys, grabbing your books, and you're on chapter 7, which is on page 249. So, guys, turn back one page to 248. That's chapter 6. What was that all about? Electrons. Now, guys, turn forward to chapter 8, which is on page 289. And what's that all about? Chemical bonds. For those of you that have already outlined chapter 8, guys, chapter 8 and chapter 9 are about bonding, and then chapter 9 is all about molecular structure. So, guys, the question then becomes, why did we skip chapter 7? And the answer is not because it isn't important. As a matter of fact, guys, chapter 7 is wildly important. So, guys, why did we skip it? You know it all already. Guys, looking at page 249, chapter 7 is all about the trends on the periodic table. And guys, we have done this stuff to death last year in general chemistry. So what we're going to do is this. You can write down what you believe that you need to, but guys, we are going to go through chapter 7 in like the next 6 minutes. So if you weren't with me and Miss Call last year, I think this should still be familiar to you. But guys, we are going to very, very rapidly review chapter 7. Then we're going to do a broad overview of bonding as we start chapter 8. And then, guys, we're going to do a deep dive into ionic bonding and talk about things we didn't talk about last year. So, guys, again, the overview goes like this. Review chapter 7. Quick overview of bonding in general, and then we're going to do a really deep dive on ionic bonding, and that's actually why you need your books, because there's a table in chapter 8 that we're going to rip apart and make sense of. So, guys, with all of that said, here we go. Chapter 7, faster than you ever thought humanly possible. So, guys, when we talk about trends on the periodic table, it is important that you understand the trends as we go down groups and as we move across periods. But guys, please be careful. When you say across, down has a direction, right? Down is from top to bottom. Which direction is across? Could be either way. Could be this way, could be that way. And guys, it is not assumed that you mean left to right. So when you talk about the trends on the AP test, you need to specify down and then left to right if in fact that's what you're talking about. So guys, the first trend that you need to know is for atomic radius. If you would like to jot these ideas in your notes, that would definitely be appropriate, but I think you know them. Guys, as you go down a group, do the atoms get bigger or smaller? Bigger. Why? Adding layers to the onion, you're adding energy levels. So guys, as you go down a group, can we just not write this down because you already know it? Is that, oh good, okay. So guys, then what about across a period? Yeah, they get smaller. And guys, think about everything that you know about Y, given the conversations we've had about PES. Right? Nuclear charge, effective nuclear charge. Those are the spikes in the PES spectra as they move to the left, closer to the stronger nucleus. So guys, as we move from left to right across a group, these atoms get smaller because the nucleus gets stronger. So guys, the atomic radius decreases due to an increased nuclear charge, and we can bring that all together with this representation where the heights of the boxes represent the radii, and as we go down they get bigger because we're adding energy levels, and as we go left to right they get smaller because of the ever-increasing strength of the nucleus. You guys good on atomic radius? Okay, so guys, why do we start with atomic radius? And the answer is because atomic radius is the predictor of electronegativity. So guys, remember electronegativity is an atom's attraction for electrons from other atoms. We think of it as being stealing power. Now, guys, the question is this. Which atoms are the good stealers? The little ones. Guys, that's why we learn radius first, because small atoms are good electron stealers. And so if you know the trend in atomic radius, you know the trends in electronegativity. So guys, as we go down a group, these things get bigger. As a result, they get weaker because you got more shielding. You've got more stuff in the way. Consequently, the atom's less likely to pull in electrons. As we go across a period from left to right, the atoms get smaller, they get stronger, less shielding, stronger nucleus, better able to steal electrons, which brings us back to that overarching idea that small atoms are strong atoms. You guys good on electronegativity? Is that okay? And then, remember the animation? Maybe? Here's the electron. Remember? Have I shown you the new and improved one?
No.
Oh, go ahead.
If you were to say steal on the AB test, like electronegativity.
That's an interesting question. So I'm trying to think of the context that they would ask you a question about electronegativity. Yeah, so I can't imagine they would mark that wrong so long as your concept is correct. I think maybe attraction might be a better term, but I wouldn't imagine they'd dink you for steal. I'd like to believe that. Okay. So guys, electronegativity goes like this. So we've got two competing atoms. We've got a small atom like hydrogen, and then we've got a larger atom like number 19, which is potassium. And guys, this is again all about the factors that are also at play in PES. So if this is an electron from one of these atoms and these two nuclei start pulling on this electron, guys, a hydrogen atom has a very small nuclear charge. It's got a Z of 1. It's got 1 proton. It doesn't have a lot of pull. But interestingly, it also has very little shielding. It's only got 1 electron that is shielding this electron, and 50% of the time on average, this electron is on the other side, and it doesn't shield at all. So we've got low shielding, but a weak nucleus. And then guys, over here, we've obviously got a much stronger nucleus, a stronger nuclear charge, 19 protons pulling on that electron, but we also have much increased shielding. So we've got these other 19 electrons pushing back. So the principle then becomes, which one of these will actually win the electron? Which one will this electron tend to, which one will steal? Which way is it going to go, left or right? Yeah, small atoms are strong atoms. You may remember the sparkle. Because that's your winner. And guys, that's really the case. That even though hydrogen has a weaker nucleus, it has less shielding, and therefore a increased effective nuclear charge. Electron goes that direction. Go ahead, Caleb.
So why would the strength of the atom be if they always have the same ratio of
Yeah, that's a good question. I like the way you ask it too. So why isn't the relationship linear? And the answer is because the distance between the energy levels is not linear, right? And consequently, the effect of that shielding is not a linear effect. And it gets even crazier because you'd even have to take into consideration the shapes of the orbitals, and at that point it really gets nutty. But that's the answer why. Because the distance isn't linear, the effect isn't linear. Yeah, it's a great question. You got on this idea of electronegativity? Okay, then guys, remember, strong is smaller, smaller is stronger. On the other side of this, we then have ionization energy, which in PES we called electron binding energy. But guys, you may remember that in the same way that electronegativity is keeping power, electronegativity is stealing power, ionization energy is keeping power, and they trend exactly the same. The same atoms that are good stealers are also good keepers, and therefore it's harder to get the electrons away. That is a higher ionization energy, which in the last unit we called electron binding energy. So guys, those are the three trends you need to know. You need to know radius, electronegativity, and ionization energy. Is that okay? Anything there you want to explore? You guys okay? Cody, did you guys do that last year with TJ? Is that good? Josh, are you good and Alice, are you guys good from your Mountain View experiences? Okay, are we settled then? Chapter 7's done and dusted? We're good? Okay, good? Okay, so guys, moving along then into chapter 8, and let's just do this so that we can transition cleanly. In chapter 8, let's go to page 293. And you can just leave your book open to page 293. We'll get there momentarily. But guys, we're now going to, for the next few minutes, do sort of a 30,000-foot review of bonds. So we're going to first of all define what a bond is, then we're going to talk briefly about covalent and metallic, and then we're going to do a deep dive today on ionic and talk about the energies of ionic bonding, and that'll then be our day. So guys, to get started, the first thing we need to do is define a chemical bond. So here's what I want you to do. In your notes, take a swing at this. Come up with your own working definition for what a chemical bond is. And guys, commit to something on paper. If you had to describe what is a chemical bond, and even if you're having a hard time putting it in sentence form, what are the words that would need to be a part of your description of a chemical bond? Kind of an interesting exercise. So guys, let's do this. Rather than have you read your working definitions verbatim, what are the terms that you found important in describing bonding? Shared, charge, between, good. Yeah, although they're not always between, you'll see. What else? Atoms, electrons, attraction. Yeah, what else, y'all? It's a good list. So we had atoms, we have charge, we have electrons, we have attraction, we have between, and we have shared. So guys, we've got all of these ideas circulating about bonding. But maybe we do this. Which of those terms is generic enough to be a part of our definition of bonding, and which of those terms was specific enough that it's describing a particular type of bonding? Like, for example, Jason, you said shared, which begs which type of bonding? Covalent bonding. Did any of those terms describe specifically a type of bonding, or were all of them generic enough that they could apply universally? So we had atoms, that sticks. Attraction, that sticks. What about charge? Does charge stick universally? It actually does. Yeah, we'll look in a minute. Guys, what else? What else did we say? Between, kind of, although you're going to find out there's a type of covalent bond that is not in the bond axis. It's actually outside of it, so it's not technically between. But I think we can leave that in the list. That was pretty good. So guys, let me give you our working definition for bonding. This is not, I mean, this is one, there's many ways to say this. But guys, what I'd like to do is allow you the opportunity to write it down, but also the opportunity to see where your words fit into this model. So this is going to be our working definition. A chemical bond is a force of attraction between two atoms, which occurs when two atoms or ions are strongly attracted coulombically to each other. Who was it that came up and asked, what does coulombic mean during the test last time? Was that, what does that mean? I told you, right? Did I tell you? Okay. So guys, again, a force of attraction between two atoms which occurs whenever two atoms or ions are strongly attracted coulombically to each other. So guys, let's look for our words. So we had atom, that's obviously there. Between, kind of, what else did we have? None of us meant, okay, charge. Guys, where is charge in this? It's actually the word coulomb, coulombically. Guys, the word coulombic means an attraction between dissimilar charges. If that's causing you sort of a little bit of confusion relative to covalent bonding, we'll talk later. So what other, none of us mentioned force. I found that was interesting. Guys, this attraction, this thing that we call bonding, is a force of attraction. It's an electromagnetic, a coulombic attraction. But are we okay with this being our working definition? Okay, the question then becomes, how does this play out? How does this attraction get created in all the different scenarios that we know? And guys, there's only three that you need to keep track of: ionic, covalent, and metallic. So what you need to be able to do is find these bits in an ionic, a covalent, and a metallic setting. So guys, maybe what we should do is first of all talk about, we've got the staircase, right? And what are these? Metals, and these are the nonmetals. So if we get a metal and a nonmetal together, what kind of bond are we going to get? Ionic. How come? What do we know about the metals? Big and fat and weak. Nonmetals, small and strong. And we end up with ions being formed. That would be an ionic bond. Is that sounding familiar? Okay. So then, guys, what about nonmetal to nonmetal? That'll be covalent because you have two small, strong atoms fighting over the same electrons. Because neither one wins, they end up sharing, as Jason said, and there we get a covalent bond. But guys, this brings up a really interesting question, and we'll dig into this more later. But guys, when we say covalent is sharing, sharing what? What's being shared? Electrons, right? And we even draw it like this. Like when we talk about water, we draw bonds that look like this. But guys, what do those dots represent? Electrons. And what do electrons do to each other? Yeah. So why does that create attraction? Interesting, none of you asked last year, right? Guys, you just take this at face value and you never question it. But why on earth would pairing two electrons together, which is by its very nature repulsive, why would that create attraction? And guys, it's not some sort of weak, wimpy attraction. Covalent bonds are stronger than ionic bonds. So how on earth does that pairing, which does in fact create repulsion, how does that create very strong covalent bonds? We're not going to talk about it today. We'll talk about it Friday. But I know, right? But it does bring up an interesting question. And then, guys, finally, the last one. Sorry, don't do that. When I clean up, it now clicks for me, which is really annoying. Then, guys, the last type of bond that we need to talk about is metal to metal, which is what? Metallic. And we are going to talk about that today. But, guys, the trick is, in each of these types of bonds, you need to be able to find the attraction. What is being attracted to what in covalent, ionic, and metallic bonding? Is that okay? Okay. So guys, with that said, we're going to do a quick review, and then we're going to dig in deeper. So I don't think you need to write this down. Slow me down if you do find any of this going, oh my gosh, I forgot that. But guys, when we talk about bond types, the first type we have is ionic bond. What atom pairing creates an ionic bond? Metal to nonmetal. What does the nonmetal do? The guy on the right. What's he do? Takes in electrons. What about the metal? Gives them away. Remember, big and fat and weak, small and strong. Transfer of electrons creates ions, and those ions attract each other. So guys, the idea then, this should sit well for you, is the idea is an ionic bond is a coulombic force that exists between ions. So there's our attraction. It exists between ions. It is a metal and a nonmetal, and this forms when the nonmetal steals the electron from the metal. This creates ions, which then attract each other. Is that all sounding very familiar? Okay, well guys, what you're going to find out today, and don't write this down, this is what we're going to do for the rest of the day. There's one missing step. This is what you learned last year. You learned about stealing. You learned about the attraction of the ions. Guys, today what we're going to do is we're going to paint the whole picture, and we're going to talk about lattice formation. It's really interesting. And we'll get to this is the last thing we're going to do today. For now, you should just know this stuff. Is that okay? Okay, so then, guys, similar conversation relative to covalent bonding. So covalent bonding happens, as Jason said, through the sharing of electrons, which now I hope you understand is counterintuitive, because electrons, they repel, they don't attract. So how does that create a bond? And we'll talk on Friday. But guys, this happens with two nonmetals, and the process of formation goes like this. Up till now, you guys understand that this is about sharing. But in the same way that ionic bonding involves this lattice formation that we haven't talked about before, there's another thing that you're going to learn about covalent bonding that you didn't know about before, which is hybridization. And guys, we're going to teach this in a week and a half or so. It's fascinating. It turns out that when every atom but hydrogen bonds covalently, it actually goes through a process beforehand called hybridization. And it explains so much stuff that you know to be true about molecules. It's really cool. You're going to like this day when we talk about hybridization. But understand that before they can share, everybody but hydrogen has to hybridize first. And we're going to add that to your understandings this year as well. Okay, so we've got ionic, we got covalent. What are we missing? Here we go. So guys, metallic bonding. This is it. This is everything that you need to know about metallic bonding. We are not going to come back to this again. Guys, so if you want to write this down because you just don't remember, this is the end of our conversation for the rest of the year about metallic bonding. But guys, rather than just give it to you, I think if you can think through this, you'll remember and understand better. So guys, obviously metallic bonds are formed by metals, but what do you know about how they react? Big, small, strong, small, weak, what's the deal? They're big and weak, right? So if you get a bunch of metal atoms together, what do those metals want to do? Give away electrons. How many valence electrons do they have? Not very many, right? You've got 1, you've got 2, you've got essentially 2 for these, because these are in the D's and the F's. Guys, they basically have 1 or 2 valence electrons, and they don't have a very good hold of them. So when you get a bunch of metals together, they just go bleh, and they start spitting electrons everywhere. Guys, that's what makes metals really good conductors, right? Because what is electricity? It's a flow of electrons. And that's why metals are really good conductors, because they freely just give away electrons, and that creates current. But here's the interesting question. If the metal atoms are giving away electrons, who's picking them up? Nobody. Remember the sea of electrons. And guys, that's the idea. So a metallic bond then is defined as such, and you can write it down because again, this is our only time we're going to talk about this. Guys, a metallic bond is defined as a delocalized bond that exists between metal atoms which have low electronegativities and very few valence electrons. The key word here, guys, is delocalized. Metallic bonding does not have position. If you look at a water molecule, you know where the covalent bonds are. If you look at a salt crystal, which I may as well grab because we're going to be doing this later. If you look at a salt crystal, you know where the bonds are. In this case, ionic. In this case, covalent. But you know where the bonds are. Guys, the bonds in metals don't have location. They are delocalized. And that's where we get the idea of a sea of electrons. So guys, each of these atoms is then bonded or attracted to many of its neighbors, but the electrons that form these bonds are free to move throughout the substance, which again is what makes these things great conductors. And so guys, we have this model of the sea of electrons where you have these positively charged atoms because they've lost electrons, all being sort of generically attracted to this negative electron field. And you end up with these bonds, if you will, spread all throughout the substance. And it's what gives metals all of its really cool properties. Yeah?
So like with that separation,
Mhm.
the non-metals,
Yeah.
is that like a hard, like it's silicon, like is it?
No. This is interesting.
And it's
Yeah.
like gold?
Yeah, so where are the lines? And actually, the answer is even cooler than your idea, right? So you're thinking, could it be both? Could there be a substance, an atom that behaves both like a metal and a non-metal? And the answer is absolutely. We call them the metalloids. But there are actually compounds. And we don't know if it's a salt or a molecule. We don't know if it's ionic or covalent. And actually, interestingly, in some cases, it behaves as both depending upon the circumstance. It's really a leading edge in some cases in chemistry research is to fundamentally figure out whether some compounds are more salt-like or more molecule-like. Yeah, some of the coolest stuff they're doing with that right now is actually with water molecules. Because water molecules, while they do have, it's clearly covalent, but sometimes when you cool them down enough, they work like little charge packets, almost like ions. And the University of Utah is doing some fascinating research right now on sheets of ice, single molecules thick. Because if you can shave ice a molecule thick, those water molecules behave like little charge packets. And they're so polar, it's really fascinating. It's cool stuff. So anyway, and it's all computational because we can't slice water that thin, ice that thin, so it's all math. It's pretty neat. So anyway, so guys, you good on metallic stuff? You good there? Okay, so what we're going to do for the rest of the day then is we are going to fiddle around with salt. Literally, we're going to figure out what on earth is going on when sodium and chlorine come together to make salt. Now, guys, the thing that's interesting about this is we can have a conversation right now that we couldn't have had even a day ago before the test, because believe it or not, PES has a lot to do with the conversation we're about to have. So guys, let's make the transition and let's talk ionic bonding. And I think a lot of this, well, let's be judicious, but there's definitely stuff here that you're going to want to at least, tell you what, wait for a second, let me show you, and then we will pause and I'll lead you to the things that I think would be worth putting in your notes. So guys, don't write this down, but when we talk about ionic bonding, let's talk about our most familiar example, which I think we would agree is table salt. And guys, again, sodium is a metal, right? Big and fat. Chlorine is a non-metal, small and strong. Good? Okay. All right. So guys, with that said, here we go. And I think this would actually be worth writing down, but write it down off to the left. So guys, write these big, like maybe 2 lines tall, but move the sodium and the chlorine off to the left, because eventually we're going to connect these and skip down a couple lines. So guys, once you're caught up with me, let me explain to you where we're headed with this. So guys, we're going to bring to bear on this conversation the stuff that we learned in chapter 5 about endo and exothermic and enthalpy changes. But guys, we're also going to bring what we learned in the previous unit about ionization energy and electron binding energies and the release of energy as electrons move between energy levels. We're going to bring that to bear on this as well. So as we do, the first question is this: what do the dots represent? And don't say electrons. Which electrons? The valence electrons, right? Because guys, we understand that sodium has one valence electron, chlorine has 7. What about the hold that sodium has on that one valence electron? Weak or strong? Pretty weak, right? Can you picture all the shielding? Imagine the PES spectra of this. You get the one hump. It's not very tightly bound, that stuff. And then guys, chlorine, 7 valence electrons. What about the electronegativity of chlorine? High, right? It's got a good hold on those electrons. So guys, when we bring these together, what will the chlorine do to the sodium? It's going to take it away, right? But guys, here's what I want you to do. I'm going to animate it in a minute, but I want you to draw it sort of with arrows in your notes. So guys, this is the way we're going to picture this. Well, here, let me show you the animation. We've always done this like this. We've just said sodium steals the electron from chlorine steals the electron from sodium, right? So we've got this. Chlorine steals the electron from sodium, sodium positive, chlorine negative. But guys, I'm going to challenge your thinking on this. I would suggest to you that this process can actually be thought of as two steps. It can, do this with me, it can be thought of as the removal of the electron and then the capture of that same electron. So guys, removing that electron from sodium, is that endo or exothermic? Removing the electron from sodium, endo or exothermic? Endothermic. This is an endothermic process. How much energy does that require? Not a number, the name. How much energy does that require? Electron binding energy, or we also call that ionization energy. And guys, don't write this down, but can you picture it? What we're really talking about is taking that electron from energy level 3 and kicking it up to energy level infinity, right? Removing that electron from the atom, everything we talked about in the previous unit. Okay, so we understand what it takes to get that electron away. So now that the electron's been removed through the endothermic process, then the electron falls into chlorine, endo or exothermic. Exothermic. And guys, we could actually, we're not going to, but we could actually calculate the color of light that is released. And Robbie, you're right, it's not visible. But guys, we could calculate the color of light that's released because it would be from energy level infinity down to energy level 3, and we could do that math and figure out the color of light that's released. See how all of that comes from chapter 6? But guys, if nothing else, we know that the energy is being released and that makes it exothermic. Are we settled on that? Go ahead.
Could you just like take the two and add them together and figure out how much energy you receive if the reaction itself is endo or exothermic?
What's the name of that? That process of adding energies to come up with overall energies. Do you remember? Hess? Yeah, it's called Hess's law. And the answer is absolutely. If you know the amount of energy that goes into this, and if you know the amount of energy that comes out of this, the difference would be the energy that's gained or lost when sodium and chlorine makes table salt. Okay, does that make sense? Now what about this? What if this is biggest? If the what if the exo is bigger than the endo? What will the overall thing be? Exo, right? Energy will come out. What if the endo's bigger? Then it's going to be a net energy gainer. Guys, does that make sense? Because we're about to talk about that in just a minute. Yeah?
So is there no energy gain in this process? Because like it's from 3 to infinity and infinity to 3?
Great question. But why would that not be true? Why would those energies not necessarily be equal? Let her think about it. Bingo, exactly. Because it's not going from sodium to sodium or from chlorine to chlorine, the energies will be different. Go ahead.
So the Riker, the word
Yeah.
it's obviously different now. It's like,
Yeah.
is it how does it relate to that?
Yeah, so this was, that's a really interesting question. I don't want to do a super deep dive on it, but let me repeat back your question so everyone heard. So the Rydberg constant that there's the tail end of it right there, right? So the Rydberg constant that we've been talking about is the Rydberg constant for hydrogen. There are similar constants for all the other elements, but they are different. And you saw that a little bit on the test you took. Remember the question on the test that said a helium ion, when an electron falls in a helium ion, it gives off more energy than in a hydrogen atom. And the thing that the question was hoping you would understand is a hydrogen atom has 1 electron. A helium ion also has 1 electron. But because it has a stronger nucleus, when that electron goes through that same fall, and I don't remember what it was, it releases more energy. The reason is because each of the energy levels has more energy associated with it, therefore changes between them have more energies associated. And that just gets even more complicated as the atoms get bigger. The thing that's not quite comparable is the fact that you have to deal with shielding, which is why the question on the test dealt with the helium ion, because there's no shielding in the helium ion either. So, does that make sense? Was that to your question? Kind of. I did my best. So, guys, you good with this idea of energy in to remove the electron, energy out when the electron falls back in? Does that all sit okay? Yeah.
Wait, so with the helium
true.
So how are you going to calculate that?
You're not being asked to. The question on the test was qualitative. It just says, so we're not going to do that here. We're going to talk numbers, but we'll not be doing those calculations. I just mentioned that in reference to Bailey's question. All of it to say the energies are different for every atom because their nucleus and their shielding properties are different. So that was the only point. Okay. Is that okay?
Yeah.
Let it be okay. We're not going to do math. Yeah, we're never going to bring the Rydberg constant to bear on this. Okay. So guys, this then is where we are. Energy in to remove electrons, energy out when electrons fall. Is that okay? Okay, because guys, we're about to jump on what Robbie started talking about with the Hess's law thing. And guys, this creates an interesting tension. Follow the thoughts. So guys, it goes like this. So we now have this idea that chlorine picks up the electron from sodium. We understand that chlorine becomes negative, sodium becomes positive, those attract, zip, bang, pow, and we end up with table salt, right? That's what you understood from last time. This is the thing that's interesting. And guys, I would encourage you to not write this down. Just allow if you've got the arrows drawn, you have everything written down you need. But guys, we're about to create a little bit of a crisis here. And the conversation goes like this. Oh gosh. So the conversation goes like this. Guys, when sodium and chlorine react together, the reaction is very exothermic. I'm going to show you in a video in just a second. So when sodium and chlorine come together to make table salt, it is a very, very exothermic process. So let me show you what I mean by very exothermic. You guys remember this one? The idiot with the popcorn? Yeah, so let me start it. Yeah, I was afraid of that. Uh-oh. Just a second.
Stuff. You got to make it yourself. Well, how are you going to do that? Salt is sodium chloride. Sodium is a metal that explodes on contact with water.
Okay, starting
and
over.
chlorine experiments. Supposing you want some, this is one of my favorite experiments. Supposing you want some fresh salt. None of that stale old store-bought stuff. You want the fresh stuff. You got to make it yourself. Well, how are you going to do that? Salt is sodium chloride. Sodium is a metal that explodes on contact with water, and chlorine is a deadly poison gas. They actually used it in World War I as a poison gas.
So guys, for those of you that haven't seen or don't remember, here's what's going on. Down in this large crucible, there is actually a chunk of sodium metal. And then over here is a cylinder of chlorine gas, which goes from a rubber tube to a metal tube. And he's actually bathing the sodium metal in chlorine gas and then igniting it. So you literally have sodium metal burning in a chlorine atmosphere.
If you take a bowl full of molten sodium and you blow pure chlorine gas into it, you get a fire and the smoke coming off.
Like so. So guys, you can clearly see this is exothermic, right? All the heat that's being released, you could almost imagine your hands around this getting warm, all the energy that's coming out, right? By the way, interestingly, what's the smoke? It's table salt. Yeah, the smoke is pure table salt. But guys, turning our attention to the flame, to the heat, to the energy, where is that heat coming from? Look at your notes. The electrons falling into the chlorine. So guys, some energy is being recycled to kick the electrons out of the sodium, but the vast majority of this energy is coming out of the chlorine, taking in those electrons and releasing that energy as the electron falls, coming out as heat. If nothing else, you're convinced it's exothermic, right? You can see it. Okay, so continuing on then. Oh gosh, we'll let the video play out.
This is one of my favorite gas into it. You get a fire, and the smoke coming off of that is pure salt. So we hung some popcorn over it, salt the popcorn with nice fresh salt. And it worked great. We got some good shots that we used in the magazine. Then, turns out, the net started melting, and it actually...
Don't you think that might have occurred to them? Yeah. So nylon net plus flame.
Dropped the popcorn into the molten sodium. Sodium exploded, and we got popcorn and sodium flying everywhere. That's really not such a bad thing. It tells you that science doesn't always go the way it's supposed to. It tells you why it's important to wear a face shield and have all the right safety equipment.
Personal protection
And it made some really good shots that we could use also.
There you go. All right. So, guys, you're convinced this is exothermic, right? Okay. Because this is where this gets sort of messy. Guys, we understand that this process is exothermic. And again, we understand the energies involved are energy going in as sodium is ionized and energy released as chlorine picks up the electron. So we know this. And again, you've already got this in your notes with the arrows. Losing electrons is endothermic, yes? Make sure. Losing electrons is endothermic. All right. And gaining electrons is exothermic, yes? Here's the thing that's interesting, guys. When sodium chloride is formed, the losing process is more endothermic than the gaining process is exothermic. But if you tie that back to what Robbie got us thinking relative to Hess's law, we've got a problem. So guys, if you don't understand what this sentence means, let me show you. So energy goes in to kick the electron out. That's endothermic. Energy comes out as the electron goes in. Now guys, whichever one of these is bigger, Hess's law will be the one that is the overall experience. Guys, this sentence is telling you, and this is true, that this is bigger than that. Just a moment. The endothermic process, when sodium loses its electron, is more endothermic than the exothermic process when the electron is captured by the chlorine. And guys, you just need to know that that's not only true here, that is true for most ionic bond formation processes. I'm going to let you wait for a minute. Guys, the gaining of energy as the electron leaves the metal is greater in magnitude than the energy is lost when the nonmetal loses the electron. So guys, the question then becomes, how do we resolve this conflict? And guys, the answer is this. This isn't the whole picture. This is not the whole picture to bond formation, ionic bond formation. Guys, if this was it, and this is what you thought was true up until now. Sodium loses the electron, chlorine gains the electrons, positives and negatives attract. And guys, if that were the entire picture, then we could play that video again and you wouldn't see flame. It would actually get cold. You see what I'm saying? So guys, the question then is, what else is going on? And in order to show you the answer, I want to share this with you. Guys, there's another step, and it's what's called lattice energy. Guys, write this down with me. This is why that video looked like flame and not like cold. Guys, it's called lattice energy. Here's what happens. As these negatively and positively, as these oppositely charged ions, as they come together, they begin to attract each other. So guys, the thing that we saw on the screen with the arrows, the thing you wrote in your notes earlier, simply described the formation of the ions. It doesn't describe the attraction of the ions. So what's going on is this. As the attraction between these ions draws them together, there's another release of energy. And it is the release of energy as the ionic bonds form, and you end up with what we call a crystal lattice. It's what happens when this forms. And guys, that's where all the energy comes from. The energy that you see in flame in that video is not the energy of chlorine capturing electrons. It's the energy of the sodium and the chloride coming together and forming the lattice. Yeah.
Wait, but wasn't like coming off as a smoke?
Smoke was not the energy. The energy is the flame. And actually, that's not even completely true as well. The flame that you see is actually just excited air, and the energy coming off the reaction excites the air molecules, and that's what we experience as flame.
Does the lattice still exist in the smoke?
And that's the idea, that the lattice is the salt. The salt that was coming off is the lattice that was forming. Yeah. So guys, let me show you what this looks like. This is interesting. Guys, this is the entire life story of the formation of salt. This is how the whole thing goes. So guys, right here was the beginning of the video. You had the sodium solid and you had the chlorine gas. So now, step number 1 goes like this, moving up, endo or exothermic, step number 1. Endo, because we're going up. And what happened, guys, looking, and is that, here, let me zoom in more so you can read it better. So guys, zooming in there, and I want to do this. That's the best I can do, right there. Okay, so guys, zooming in here, what happened in step number 1? Focus on the sodium. The sodium melted and vaporized. Okay, so the amount of energy needed to melt and vaporize the sodium is represented there, endothermic. Step number 2, endo or exothermic. Endothermic, what changed there? The bonds inside the chlorine separate. The diatomic chlorine becomes chlorine in its monatomic form. Now guys, watch this. Woohoo! What's all that energy? It's endothermic. Thank you for staying with the trend. It's endothermic, but what's that energy doing? Ripping the electron off the sodium. Guys, it takes twice as much energy, proportionally, maybe 4 times as much energy to rip the electrons off of sodium than it does to take sodium metal and turn it into a gas. That's a bunch of energy. That's all the energy that went into sodium to rip the electrons off. So now we have sodium gas, free electrons, and chlorine gas. Now, what happens next? So this step, endo or exothermic? Exothermic, what happened? The electron got captured by the chlorine. Now guys, this is what this process looked like to you up until now. That's all that we've talked about. Chlorine gains the electrons, sodium loses them, you get ions, you get ionic bonding, end of story. But guys, if that was the end of the story, that video, you wouldn't have seen flame, that would have been cold. Guys, this is all the energy of the flame. That is all the energy that's being released during this process. And what is changing from here to there? The lattice is forming. These positive and negative ions are coming together and forming this actually amazingly repeated structure that we call table salt. And as this thing forms, all of that energy is being released, and that is the energy that we saw as the flame in the video. Yeah.
Why does the sodium where does that get oxygen?
I'm going to ask that back to you as a question. So your question was, why does their coming together release so much energy? My question to you is, why do they come together? It's even bigger than that. Why does anything happen? Gibbs free energy. Why does anything happen? It's not metaphysical. Anything that we see that happens, what do we know is taking place? It's releasing energy, right? Any process that we see happen, any spontaneous process releases energy. And so all processes in our universe are always moving to conditions of lower energy. And that's no different for this. The sodiums and the positives attract, and as they close in on each other, energy is released, and that's the energy that we call lattice energy. But really, we don't think of the cause and effect being the direction you stated it, it's the other. This is happening because it releases energy. Is that okay? Okay, so guys, this then brings up an interesting question. And this is what you need to know for the AP test. So guys, are you comfortable with this idea of lattice energy? So lattice energy is the energy that's released when the ions come together and form these repeated crystalline structures that we call lattices. Is that okay? Now, guys, again, is lattice energy endo or exothermic? Exo, energy is going down. It's exothermic. Are you settled? Guys, looking at the table on page 293, these are all lattice energies. You'll notice that you've got compounds, energies, compounds, energies. But guys, the minute your eye looks at this paper, the table, you should be sort of brought up short. Do you see the big problem with these numbers? They're all positive. And didn't we say lattice energy was exothermic? Right? We see it. Lattice energy is exothermic. And if it's exothermic, what should the sign for the delta H be? Negative. So why is it positive? And guys, the answer is this. Turn to page 292. See the word lattice energy in bold? You see it there? Okay, so guys, if you read the sentence that contains that, it says this. It says, a measure of how much stabilization results from arranging oppositely charged ions in an ionic solid. And Jason, there's another addition to your question, is it's also about entropy, right? The stabilization. So in an ionic solid is given the name lattice energy. Now guys, read. Which is the energy required to completely separate 1 mole of a solid into its ions. So guys, join me at the board. This is actually the definition of lattice energy. It's the amount of energy needed to break it apart. But wouldn't that be the opposite of the amount of energy that's released when it forms? And that's the idea. When we measure these in lab, it's easier to take the solid and rip it apart than it is take the gases and turn them into solid. But the numbers are the same, it's just the sign is different, and that's why they're positive. So, guys, with that, read this with me. Look at the table. And guys, the thing that you've got to know for the AP test is what is the magnitude of lattice energy dependent upon? What is the magnitude of lattice energy? And it's 2 things. Guys, my table looks like this, different colors, same information. What is lattice energy dependent upon? 2 factors. Charge is 1. Organization is pretty consistent throughout. It's actually, somebody said it. Size, watch. Guys, it goes like this. For example, you'll notice here, we've got lithium, lithium, lithium. The lithium atom is the constant. But then we've got fluorine, chlorine, and iodine. Guys, notice these are in order. Fluorine, chlorine, iodine. And as we go down, what happens to their size? They get bigger. And as they get bigger, it means their nuclei, these charged particles are more distant. And as they get more distant, what happens to their attraction? It goes down, so the lattice energy is lower. And guys, that just repeats itself. Here our constant is sodium. As we go down, the ions get bigger and the lattice energy goes down. Here our constant is potassium. As we go down, the ions get bigger and their lattice energy decreases. Do you see that? So guys, the bigger the ion, the weaker the lattice energy. If you can't keep that straight, you may want to write it down. The bigger the ion, the weaker the lattice energy. But now guys, look at this. These lattice energies are off the charts. What changed as we look at the right-hand column that makes them so much greater? Charge. This is plus, all of these were +1 and -1. This is +2 and -1, way stronger. This is +2 and -2, even stronger. And this is +3, -3, even stronger still. So guys, which one is the major predictor of lattice energy, charge or size? Charge. The secondary predictor is size, But guys, you'll notice that the size trend continues as well. Magnesium and strontium. Strontium is bigger than magnesium, and it has a lower lattice energy. So the size trends continue throughout, but the charge trend is the major predictor. So guys, that's everything you need to know about ionic bonding. You guys good? Get the full, okay. So this then is your homework. Something else you could include in your to-do list. Guys, we will, what is going on? Guys, we will grade this on Friday.